Let's take a look at the second section in the chemistry unit. It focuses on the mole, what it is, and how to use it. All right, so first section is just going to be on some basics. The mole, what is it? Well, it's simple. It's a number. It's a number that denotes a specific amount of things. It's like a dozen. Right? Anytime you hear the word dozen, you know it means 12. You can have a dozen of anything. You can have a dozen of donuts, a dozen eggs, a dozen people. It doesn't matter what it is. A dozen is always 12 of those things. So what number is the mole? It is 6.02 times 10 to the 23rd power. That is a mole. This is called Avogadro's constant. 6.0 times 10 to the 23rd things, doesn't matter what things, are in 1 mole. So 6.02 times 10 to the 23 things are in 1 mole. So this is 602 and then another 21 zeros after it. Things are in 1 mole. That's a lot of things. And it's kind of interesting to note, like for common size things like a mole of pens, how many pens would be a mole of pens? It'd be a lot. It's a lot of pens. Right? So some of the common mole comparisons are quite huge. The question is, why is this specific number important? This specific number was chosen because it takes about 6.02 times 10 to the 23 hydrogen atoms to make 1 gram of hydrogen. Now, when Avogadro came up with this, he was dealing with carbon. And so he found that it took about this many carbon atoms to make 12 grams of carbon. How he calculated that, I have no idea. But 1 gram of hydrogen is this many hydrogen atoms. Or you could say, since a hydrogen nucleus usually only contains a proton, it takes this many protons to make 1 gram. Neutrons are the same weight as protons, same mass as protons, so it takes this many neutrons to make 1 gram. Electrons are much, 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 much lighter. All right, why is it important? Why is the mole important? Because when we have a chemical reaction, here we have a chemical reaction. And in our chemical reaction, we have 1 hydrogen molecule and 1 chlorine molecule gives us 2 hydrochloric acid molecules. These are HCl, but it's in a gaseous form. These are a count of molecules. These count the molecules. Now, So I could say we have 2 hydrogen molecules and 2 chlorine molecules. Chlorine gas molecules gives us 4 of these molecules. Or I could say a dozen hydrogen molecules and a dozen chlorine molecules gives us 2 dozen HCl molecules. But there's a problem. We can't count molecules. We can't count molecules. They're too small. We can weigh substances. So what the mole does is it gives us a way to convert from the weight to the count of molecules. So the mole gives us a way to convert from the weight of a substance to a count of molecules. So that's what the mole does. The mole says if I have 2 grams of hydrogen gas, that's going to be 6.02 times 10 to the 23 hydrogen molecules. Now I have a count of it. So I can weigh out my hydrogen gas and I can know relatively closely how many hydrogen molecules I have, so that I can compare them in a chemical reaction, because these are counts of molecules. So I need to know how many molecules. Now, when we deal with chemical reactions now, often we just say this is 1 mole of hydrogen gas, 1 mole of chlorine gas, to 2 moles of HCl molecule, and we just make it easier on ourselves. It's 1 mole to 1 mole to 2 moles, which maintains this relationship as a count of the molecules. All right, so now the use of measurements such as MASH to indirectly count a large number of objects is important. This is 1 mole of each of the following substances. So you can see table salt, that's about 1 mole of table salt. I mean, it's close. You can't measure it precisely to get it precisely enough to get exactly 1 mole. So it's close enough. This is 1 mole of sulfur, 1 mole of sugar, 1 mole of mercury 2 oxide, 1 mole of copper, 1 mole of copper 2 sulfate pentahydrate. All of these have different masses. They all have different volumes. But it allows us to count molecules, 6.02 times 10 to the 23 molecules at a time, by weighing a mass. All right, so what should you know how to do already? From grade 10. You should know how to find the molar mass of elements and molecules. Convert from mass to moles and back. So find the molar mass of lithium. So here we're going to need our periodic table. Lithium is just Li, so we're figuring out the molar mass of lithium. And we go on here and we look right here, 6.941 grams per mole. 6.941 grams per mole. So if I want to have 6.02 times 10 to the 23 lithium atoms, I need to measure out that much lithium. Now, it's not going to be precise. It's going to be close to 6.02, but I need to measure out that much lithium to get 1 mole of lithium. All right, so lithium was easy because you just read it off the table. Let's look at the other ones. Sodium nitrate. Sodium nitrate, the molar mass of sodium Na, that has a 1+ charge. And nitrate is NO3 that has a 1 minus charge. So now to figure out the molar mass of the whole molecule, you have to do each thing individually. So sodium, Na. The molar mass of Na is 2.990. 22.990. 22.990. That's for one atom of Na, and there's only one atom of Na, so we multiply it by 1 to get 22.990 grams per mole for the sodium in there. Then we do our nitrogen, and our nitrogen's over here is 14.007. 14.007 times 1, because there's only one of them, to get 14.007 grams per mole. Last one is oxygen, 15.999. Some periodic tables have it as 16.00, but we're going to do 15.999, and there's 3 of them. So you have to multiply it by 3, because it's O3. And we get a number. That requires use of a calculator. So here we go. 15.999 times 3 is equal to 47.997 grams per mole. So the total molar mass for NaO3, NaNO3 is that plus 14.007 plus 22.990. 84.994 grams per mole. So we get our NaNO3. We want to figure out, we need 1 mole of NaNO3. We need to weigh out that much NaNO3. Next one, sulfur dioxide. Sulfur dioxide, we're going to figure out the molar mass of sulfur dioxide. So S, I'm not going to show you the table anymore. It's 32.066. And there's 1 of them, so we times it by 1 to get 32.066 grams per mole. For the O2 part, 15.999 times 2, because there's 2 of them, to get 31.998 grams per mole, for a grand total of 14.15.0, carry the 1, 64.054 grams per mole. That's the molar mass. If I have sulfur dioxide and I weigh out this much, I will have 1 mole of sulfur dioxide. Next one, nitric acid. Well, this is a Rule 2 acid, so it's nitrate. And nitrate is a NO3 1 minus. So this is going to be HNO3. So we're figuring out the molar mass of HNO3. So H is 1.008 times it by 1 grams per mole. N is 14.007 times 1, 14.007 grams per mole. And the O3, you can look above to get it, 15.999 times 3 is equal to 47.997 grams per mole. Add this all up, 1422, carry the 1 is 0, carry the 1 is 0, decimal, carry the 1 is 4, 5, 6, 13, carry the 1 is 63.02 grams per mole. All right, so if I want 1 mole of nitric acid, HNO3, I have to weigh out that much of it. All right, so we can convert, so this is important, we can convert from mass to moles and back using the molar mass. That's an important conversion. because we need to use moles in our chemical reactions because we have to count the atoms, but we can't count them. So we use the mass and the molar mass to figure out how many moles there are. So we can convert from mass to moles and back using molar mass. Likewise, we can convert from volume of gas at standard temperature and pressure to how many molecules there are in that gas. So we can go from volume to moles and back by using 22.4 liters per mole at STP. So at standard temperature and pressure, it's just a standard temperature and a standard pressure to measure the gas at, because it'll be different for different temperatures or different pressures. We use 22.4 liters in 1 mole at standard temperature and pressure. And in this course, we're always going to talk about at standard temperature and pressure. So how many moles of hydrogen gas are there in 100 liters at standard temperature and pressure? So we have the volume, and we are going to go to the moles. I'm writing out my map. The volume is 100 liters, and we're going to use our 22.4 liters per mole to get to our number of moles. What I don't know, I put on the top. So how many moles are in 100 liters of H2 if 1 mole of H2 is 22.4 liters? So I do 100 times 1 divided by 22.4. So clear, 100 times 1 is equal to 100 divided by 22.4 is equal to 4.46. 4.46 moles of H2. Now I rounded that, and we're going to have to start talking about significant figures soon. So we have the correct number of significant figures. So I went from volume to moles. So 100 liters is 4.46 moles. So I made my map here. Started with that. I used my conversion of 22.4 moles per liter to get 4.46. Right, if 22.4 liters are in 1 mole, it makes sense that there's about 4 moles in 100 liters, right? Because 100 liters is 4 times that amount. Now, what is the mass of the hydrogen in the gas? So we figured out the volume. So we used the volume to figure out the moles. Now we can do a second step in this. We can go from our moles of H2 to our mass of H2. We know our moles is 4.46 moles of H2. Now we can use our molar mass of H2. So our molar mass of H2, I'm just going to write over here, molar mass of H2 is equal to 1.008 times 2, which is equal to 2.016 grams per mole. So we're going to use this conversion of 2.016 grams per mole to calculate our mass of H2. So how did I do that? I don't know my mass. So I put how many grams of H2 are there in 4.46 moles if I know there are 2.016 grams in 1 mole of H2. Now I can just solve this proportion by taking this number multiplying by 2.016. Now I've kept this number in my calculator. As I go along, I like to keep the number in my calculator in the full form. So I do 4.46 times 2.016. I got exactly 9. That's pretty trippy. So 1 mole, so the number of grams is 9. So my 4.46 moles will give me 9 grams of hydrogen gas. So that 100 liters of hydrogen gas at standard temperature and pressure turned out to be 9 grams of hydrogen. All right, so you should know what a mole is. This Avogadro's constant. You should know that in chemical reactions, we often refer to these as moles. 1 mole of H2, 1 mole of Cl2 gives us 2 moles of HCl. 1 mole is a way so we can weigh things and get a count of the molecules in them. You can figure out molar masses to convert from mass to moles and back. And you can use 22.4 liters per mole to convert from volume to moles and back. Right? And you should be able to do this work here. All right? So thank you for watching.